student friends, I'm back again with another video on Fourier transform and momentum wave function. As we have seen in the last video that while discussing the wave function of a free particle, the conception of initial wave function and some expressions to find the total wave function in the time dependent case was important, where we find the equation like psi xt equal to integration of phi k exponential to the reverse few terms depending on space and time, and some or integration over some dk. So k was some wave vector. So this particular thing need to make us that we have to understand some kind of transformations which will be known as Fourier transformation, as well as we will also know about what kind of space are there in explaining the things. So let's proceed with this video and with the conception of configuration and momentum space. The configuration space is nothing, it's a position space, or the familiar position space where we discuss the motion of the particles and everything. But apart from that, we have also momentum space, energy space, angular momentum space. So every variable can be made to have some kind of space. And with the idea of some transformations, this we can switch back from one space to another. That's like configuration or position space to momentum, or vice versa, or momentum space to energy space, like that. All the observational quantities in quantum mechanics are linear Hermitian operators, which we'll discuss in later course of time. And in the sense that it's important that the physical system can be explained in different kinds of space, like position, momentum, etc. And regarding this problem, the most convenient one that we will discuss is that how configuration space kind of things can be switched to momentum space. And the need for that is that we must have a transformation, and this transformation is known as Fourier transform. As you are quite aware in your mathematical physics course about Fourier transform, this Fourier transform is one of the basic and elegant technique to relate a function in two different domains or spaces. We can relate one thing in configure space to another thing in position space. And the advantage is that it's in quantum mechanics, the dynamical variables are simply linear operators, and all the transformations are linear transformation without any kind of high degree of transformations. So just recalling back that in the case of wave function of a free particle, here we will show you how that momentum space wave function is here, or that momentum space wave function can be converted to position wave functions. And this is the technique. Then the technique is that Fourier transform can transform wave function in position space to equivalent momentum wave function, or vice versa. And usually once we use a Fourier transform from, suppose, in transforming the wave function in position to wave function in momentum, the inverse way is known as that inverse Fourier transform. So with some typical problems we can gain the knowledge about all these things. So let's start with rewrite the forms for a wave function in case of a free particle. This is already we have encountered in the earlier video, where this is the initial wave functions, where phi k is the wave functions that contain over which is a function of this continuous variable k, and k is representing the wave vector related with the free particle. And this phi k is nothing. If we remember those equations there, this phi k can be converted back like this. Now these equations are simply Fourier transforms. This phi k is the Fourier transform of psi x0, or you can say that equation 1 is representing the inverse Fourier transformation for phi k. So just you see that this psi x0 is simply a wave function in position space, and this phi k is a wave function in k space, and this equation 2 phi k is in k space, and this psi x in position space. And later on course of time we'll see that this k is nothing, actually it is representing momentum space. This equation 1 can be written like this. it is ikx is here, and instead of this we also put a symbol here ux, that's as usual. The psi x0 is always representing the time independent wave function, so we are like this. It is simply the equation 1. Now multiplying this equation by this and integrating between this limit minus infinity plus infinity, on the left hand side we are left with this, and on the right hand side we are like this. But from the definition of Dirac delta function, del k minus k dash is equal to this. So here we find that there is a function here, e to the power ix k minus k dash dx, and there is a factor is 1 by twice pi, because square root of twice pi, square root of twice pi make is twice pi. So this gives us del k minus k dash. So one of the property of Dirac delta function is that if fk is a function and this del k minus k dash is the Dirac delta function, then it's converts back to fk dash. So using equation 5 in the right hand side of equation 3, this phi k is fk here, and this is already the Dirac delta function. So this will be converted to phi k prime or phi k dash. So the left hand side is now equal to phi k. Okay, then dropping the prime sign, since it is an arbitrary function here, we can drop this k dash here. So ultimately we are left with phi k equal to this, and since ux is nothing, it's phi x0, so it's simply phi x0 as we see in the equation 2. It is nothing, it's equation 2. And we note that the wave function in position space is given by equation 1 is now being changed to wave function in k space given by equation 2 through the use of Fourier transform. Okay, this is already discussed, I am repeating again and again. So this is equation 2, and we started with equation 1 here. So this was equation 1. This is now being obtained with the help of this kind of concepts here, equation 3, 4, 5, and the definition of Dirac delta function. Now to get back the momentum wave function in the opposite way, what we do is that we again put like this. This is, since p is equal to h cos k, we can put equation 1 in this form. We simply kx was there, so instead of k we put p by h cos here, and this is nothing, equation 1 in the form in terms of p. And again using the Fourier transform, the momentum wave function or the wave function in momentum momentum space is this simply, and ux equation 7, and just we can conclude that if ux is equal to this, the wave function in position space, this is the wave function in position space, then using the Fourier transform we get the wave function in momentum space like this. And to get back from one from the another, that means from this phi p to ux or psi x0, we have to take inverse Fourier transform, and we'll get back then this ux. So we started with these equations, this equation, and then with this kind of mathematical simplifications and the definition of Dirac delta function and its property, we come to the conclusion that we can get a momentum wave function or the wave function in momentum space from the wave function in position space through these equations. This was already done in case of free particle case, and equation 6 and 7 are nothing. It is simply this equation. Only thing is that this k is replaced by p by h cross, and although this h cross is present because of p is equal to h cross k. So with this we're left with assessment and what is momentum space, how it differs from configuration space, why we need it. This is already in the first slide of this video. And then what is Fourier transform, what is its need, and then what is Fourier inverse Fourier transformations. These things are already in your mathematical physics course also, and also the wave function for a free particle in momentum space, starting from the wave function in configuration space. So these things have been well done in this video. Hope that this video is very enjoyable for you. Keep watching our videos and also suggest for further improvement. Thanks for watching. Bye.